In this online lecture, we're going to discuss the diazonium salt formation mechanism. And what we're going to see here is that key point number 1, the diazonium salt formation mechanism involves addition of NO, followed by a series of acid-base reactions that turn the oxygen to water and creates a triple bond between the two nitrogens. The water is then booted off as a leaving group. We're also going to see number 2 is that diazonium salt formation is only possible with primary aryl and alkyl amines. So let's dive into this here. Remember, what we've learned so far is that to create a diazonium salt, you need an NH2 on a benzene ring, you're adding NaNO2 and HCl, and that gives you this right here, the diazonium salt as a product. Now, to understand the mechanism behind this reaction, let's first talk about how the NaNO2 and the HCl react with each other. That's where this mechanism begins. So let's look at that here. And what I'm going to do is write out the NaNO2 group in its Lewis dot form right here. So here's the first step of the mechanism. One of the oxygens on the NO group gets protonated by the HCl acid. So this is just an acid-base reaction. What we end up with is this as a product. Then another HCl in solution protonates that same oxygen again. That turns him now into water, which remember is a much better leaving group. And that's exactly what happens here. Water is booted off as a leaving group, so you're ending up with water as a product, and what's left over here is the NO group, giving the N a positive formal charge. This thing is called a nitrosonium ion. So going back to the big picture here, all we're saying is that the NaNO2 reacts with the HCl to create this NO positive group here. And it is this thing right here that is now ready to react with the benzene ring with the amine on it. So let's look at the mechanism of how this is going to happen. The first step here involves the NH2 group on the benzene ring being attracted to this positive and creating a bond between the two nitrogens, giving us this result right here. Take a few seconds here to make sure you see the actual matching up here of these two molecules. Now let's do this. The NH2 group in our product here, let's expand out these two hydrogens to get a better look. This sets us up for the next step of the mechanism. What we then do is add some sort of base here, doesn't matter, there's a base in the reaction that comes along and rips off this hydrogen right here and leaves the electrons behind on that nitrogen. We end up with this as a result right here, which happens to be called a nitrosoamine. And the mechanism keeps going here. At this point, we add an acid. Now careful here, I'm going to be generic. I'm just going to call it HB. Remember, our diazonium reaction is run in HCl, so there's plenty of acid available. And watch what happens here. The electrons on one of the nitrogen here fall down between these two nitrogens, and the pi electrons in the NO bond go out and grab this hydrogen right here, causing the electrons between H and B to jump up on the B. What we end up with is something that looks like this. And since our HB donated a proton to the molecule, here's how he exists right now, as B-. And the reason why that's important to know is watch what happens here. Now that he's B-, what he does here is grab off this next hydrogen right here. And again, same kind of step here. The electrons jump up on this nitrogen right here, and you're ending up with this as a result. And as a side product, since we added the hydrogen back to the B, he's now back to being HB. The molecule we've created so far in the mechanism happens to be called an N-hydroxyazo compound. But we're still not yet at the diazonium. Let's keep going here. Right now, remember, we still have our HB. What happens now is we protonate again this oxygen right here, and the electrons between H and B, of course, jump up on the B, and now our OH has been turned into water. Which, remember, we've seen this many times in organic chemistry mechanisms. Anytime we're turning OH into water, it usually means that he's being prepared to leave. And that exactly is what happens here. In the next step of the mechanism, the electrons on the nitrogen right here fall down between these two nitrogens and boot off water right here. And at this point, look what we have here, the diazonium ion. And as a side product, we would have the leaving group water right here. So what you saw here is the overall mechanism for diazonium salt formation. Remember, we showed in the mechanism how the diazonium ion is formed, but remember, since this reaction involves HCl, the Cl- in the reaction would of course be attracted to the diazonium ion, therefore making the diazonium salt. Now, you might be thinking to yourself, that's a lot of steps and that's a pretty hardcore mechanism, which it is. But let me show you how to memorize the mechanism if you have to on your orgo exam. The first thing you'd have to remember is that the actual species that reacts with the benzene ring with the NH2 group is the NO plus group here on the right, and that this is how they first connect to each other to make this product right here of this step. And remember, let's expand these hydrogens right here, and here's the key to remembering the mechanism here. All that is really happening here, the big picture, is remember we have this base B- here, and what he does is simply remove these two hydrogens right here overall. He takes them off like this, and then simply puts them back on the molecule, but at a different location, and that is on this oxygen right here, so that he could become water. Then eventually what happens is, the two nitrogens right here, remember, we got to get a triple bond between them to make the diazonium. So eventually, steps in the mechanism create a triple bond between these nitrogens and leave behind just a single bond between this nitrogen and the water. And again, since the water is a good leaving group, we eventually boot him off like this. This creates our diazonium ion. If you remember that this is what's happening overall, it could help you remember the individual mechanistic steps that are necessary to get to this result. Remember, we learned in a previous online lecture all the mechanistic moves that are possible in organic chemistry. And we also talked about how seeing what's in front of you and knowing where you're going could help you get through a mechanism. So that's our mechanism again for the diazonium salt formation. Now, some other things I'd like you to know here just in case is that you don't have to have a benzene ring to make a diazonium. For instance, this is just a simple alkylamine. Notice if I use the same reagents right here, NaNO2 and HCl, you can actually turn the NH2 group into the diazonium salt. So again, the benzene ring is not necessary for this reaction to take place. But however, there are some restrictions here that I'd like you to know. In order for a diazonium salt to form, the amine has to be at least primary. And remember, what that means is that the nitrogen has to have two hydrogens and only one R group connected to it. And we can see that that R group could be a benzene ring or an alkyl group. So that means primary amines only. So if, for instance, look at this molecule right here, notice that nitrogen has only one hydrogen and two R groups. Two R groups make him a secondary amine. If you try to form a diazonium salt with this molecule, again adding the NO plus group here, the nitrogen will still attack the other nitrogen here and create this thing right here as a result. And if you add a base to this right here, he'll still rip off, remember, this hydrogen right here, and the electrons will fall on this nitrogen like this. This gives us this product right here, a nitrosoamine. But here's what we're learning. The reaction stops at this point. Think about it. You don't have another hydrogen to rip off and therefore put on the oxygen so that you could turn the oxygen into water and boot him off. So just know that secondary amines will not form a diazonium salt. And I'd like you to know that this is also true for tertiary amines. In this particular case, when you add the NO plus group here, the nitrogen tries to attack this nitrogen here and make a connection to make this product right here. But notice in this case, there's no hydrogens to rip off that nitrogen with the plus charge. So what happens here is that this bond breaks and lets go, which means we go right back to where we started. So this is why the diazonium salt can't form for tertiary amines. But just in case, I'd like you to know what can actually happen here instead. Remember, the NO plus group that we're adding is technically, because of his positive formal charge, an electrophile, which means the NO plus and the benzene ring on the left can participate in an electrophilic aromatic substitution reaction, EAS, with again the NO acting as the electrophile. And remember, nitrogens on a benzene ring are ortho-para directing activators. So the NO electrophile will add either ortho or para to this ring. If given the choice here, in this case, we'd prefer the para product because having those methyls on the nitrogen is slightly bulky, so the NO group would prefer to be far away from that as possible, placing him para to the NCH3 group. So what have we learned here? Key points. Number 1, the diazonium salt formation mechanism involves addition of NO followed by a series of acid-base reactions that turn the oxygen into water and creates a triple bond between two nitrogens. The water is then booted off as a leaving group. We also saw that number 2, diazonium salt formation is only possible with primary aryl, and that is primary amines that are on benzene rings, and primary alkyl amines.